Hello friends, welcome to PG department of LJ University. This is a lecture series of subject Applied Mathematics for the first semester student in Computer Engineering branch. Here I, Dharmin Patel, presenting a video lecture on the topic Gradient and Directional Derivative from the unit number 3 Multivariate Calculus. This is a application of partial derivative and it is very useful for the any engineering branches. So let us start with the gradient of scalar valued function. Let phi from r cube to r be a scalar valued function. That means it is a function of two or more variables. Then the gradient of that particular scalar valued function phi is denoted as GRAD, gradient of phi or del phi. This triangle is known as the del operator for the gradient function, and gradient of phi defined as del phi by del x I caret plus del phi by del z del y j caret plus del phi by del z k caret. And when we apply our function phi on this del operator, then we get the new vector quantity, and this vector quantity is known as the gradient of a scalar valued function. So that is nothing but one mapping from vector to scalar function. That means the scalar valued function converted into the vector function. Now we will understand the geometrical concept of the gradient for particular function phi of x, y, z equal to k. If we are taking the phi of x, y, z equal to some constant, then it will be a equation in three variables, or it is represent a surface in a r cube or surface in a space r cube. Here gradient of phi is equal to del phi, and that can be written as del phi by del x. That means the partial derivative of phi with respect to x I caret plus partial derivative of phi with respect to y j caret plus partial derivative of phi with respect to z k caret. And we know that it is a vector quantity and it's represent some vector in r cube. But which vector it's represented? So now the gradient phi of xyz. Now suppose phi of xyz be a level surface in a r cube space, and p of x0, y0, z0 be any point on the surface. In this case, gradient of phi denotes the vector which is at that point, and this vector is known as normal to the surface phi of xyz equal to k at a particular point x0, y0, z0. Here it is denoted as n bar, and normal vector to a surface phi of xyz equal to k at a particular point x0, y0, z0. It is nothing but gradient of phi at a particular point p. It is also denoted as del phi at point p. Generally, the direction is depends on the partial derivative of our function. Now we want to find the unit normal vector to a surface, and it gives the maximum rate of change of phi in the direction of normal vector. So n caret is equal to del phi by del phi at p upon length of that particular del phi vector. It is known as the unit vector to a surface at point p. So now we will see some example related to this topic. Here we have to find the unit normal vector to a surface x square y plus z square equal to 2 at a particular point 1, 1, minus 1. If we put the values of 1, 1 and minus 1 in this equation, we get the right hand side equal to 2. So that is, this point is on the surface. Now, we first find the phi of xyz, which is x square y plus z square equal to 2, which is a level surface in R cube. Our fixed point on the surface is 1, 1, minus 1, and unit normal vector to a surface is equal to del phi at point P, and del phi at point P is n caret. So first of all, we will find the gradient of phi. That means the del phi at a particular point P, 1, 1 and minus 1. So that is our partial derivative of phi with respect to x and partial derivative into I caret plus partial derivative of phi with respect to y into j caret plus partial derivative of phi with respect to z k caret. Now 2xy I caret plus x square j caret plus 2z k caret, which is our partial derivative. So our gradient at point P is 2i plus j minus 2k, which is our normal vector to a surface. But we want to find the unit normal vector, so we will find the length of that particular vector. Now we want to find the unit normal vector of our normal vector, which is n bar, which is 2i plus j minus 2k upon length of that particular vector. Now we will identify the length of that vector, which is 4 plus 1 plus 4. That means 2 by 3 I plus 1 by 3 j minus 2 by 3 k, which is our unit normal vector to a surface x square y plus z square equal to 2 at a particular point 1, 1 and minus 1. Now we will discuss the directional derivative of our scalar value function. So what is the directional derivative? We will understand by definition. Let phi be a function of 3 variable and it's represent the level surface in a R cube, and x0, y0, z0 be a particular point on that particular surface. Now the directional derivative of phi at point P in the direction of particular vector. Here our vector is denoted as d bar equal to di caret plus d2j caret plus d3k caret. So its notation is like this: d capital D phi into at point P into d bar, that means del phi at point P dot product with d caret. So here our del phi at point P is the gradient of that particular function, and d caret is our unit vector of given direction. Now we will see some examples of this directional derivative. Here we have a function x square plus 3y square plus z square at a point 2, 1, 3. In the direction here a bar is I minus 2k. Now we will first find the definition of directional derivative, that is d phi in the direction of d at point P is del phi, that means the gradient of phi at point P dot product with d caret. Here we have a function phi which is our scalar valued function, and we will find the gradient of it, and direction is already given. Here d bar is our a bar. Here our function is given x square plus 3y square plus z square, and point is 2, 1, 3. Direction is a bar, which is I minus 2k caret. So a caret will be, we can find the length of that vector, which is under root 5. So its a caret will be 1 upon root 5 y caret minus 2 upon root 5 j k caret. Here we will find the directional derivative. So first of all, we will find again gradient of phi. So here gradient of phi is nothing but del phi at point P, and it is given by the del phi by del xi caret plus del phi by del yj caret plus del phi by del zk caret. So here we calculate it. So it will be 2xi caret plus 6yj caret plus 2zk caret, and now we will put the point 1, 2, 1, 3 in this point particular gradient. So we get the del phi at point P is 4i caret plus 6j caret plus 6k caret, which is our normal vector. And now we will find the directional derivative by the given formula, which it is a dot product of gradient vector with d caret. Here already we found out the d caret. So our formula is this: a caret dot product with gradient. So finally we first write down the gradient and its dot product with the a caret. A caret is 1 upon root 5 and 2 minus 2 by root 5. So after simplifying we get the 8 by root 5 minus 8 by root 5, which is our directional derivative of given scalar valued function in the direction of I minus 2k. And now we will discuss the tangent plane and normal line. It is also similar to gradient and directional derivative. So here phi be a level surface and it is denoted as phi of xyz equal to k. It is a level surface in vector space R cube, and P be a any point, fixed point on this surface. X0, Y0, Z0 are coordinate of that particular points, and equation of tangent plane is given by partial derivative of phi with respect to x at point P, x minus x0 plus partial derivative of y at point P, y minus y0 plus partial derivative of phi z into z minus z0 equal to 0, and equation of a normal line is given by x minus x0 upon del phi by del x at point P, y minus y0 upon del phi by del y j P at point P, and del z minus z0 del phi by del z at point P. So that is our normal line in a vector space. So this is our level surface, and P be any fixed point on the particular surface, and tangent plane is given by this equation, and normal vector is nothing but gradient, and the normal line is given by this equation. So that is the concept of partial derivative we will use at gradient, directional derivative, and in the tangent plane and normal line. Now in the next lecture we will cover the optimization of multivariable function. Thank you very much.